more talks before we have the discussion, also the virtual visit to the Sardinia radio telescope, which I'm quite curious about. But so we'll start with T.Dauser, who's going to be talking about this question that came up yesterday with Riley and other people about return reflection, returning radiation and reflection. And you have the floor. Go ahead.
Thanks. Good morning, everyone. So Riley already advertised this talk, and so I'm also very excited to be able to tell you about this study, which in my opinion is the first generalist study on returning radiation and how it affects relativistic reflection. In order to also increase your interest, maybe upfront already, I'll give you one of the main conclusions just right in the beginning, which is, so I'll show you that for very high black hole spin, returning radiation actually dominates the relativistic reflection spectra. And I think that's a big thing. So, but first things first, I'll start with a very brief introduction slide to bring everyone on the same page. So here on the left-hand side, you can see the picture we generally have in mind, and we have seen it very, very often. So we have coronal emission here shown in blue, irradiating the inner part of the accretion disk, and due to GR creating reflection there, and due to GR effects and the very rapid movement of the accretion disk, this reflection is distorted, and then we can observe it. And farther outside, we also see distant reflection, and this I will not talk about right now. But what is obvious to probably most of you, but I still want to stress it, that we'll need to model the detailed shape of this reflection in order to measure the important parameters we're interested in, like the black hole spin and the location of the corona. So a detailed model here that we understand is of importance. So let's zoom in into this picture. And returning radiation is now, what I mean by returning radiation is that part of the coronal emission is producing reflection, but this reflection might not go to the observer, as you can see on the left-hand side, but it might be bent back to the disk, producing then what you can also call secondary reflection. And this is then observed as well as also relativistic reflection. And I want to stress that, well, it has been studied in part by a few publications before, but it's completely neglected in modeling, and also the effect on relativistic reflection hasn't been looked at. So I want to show you in the next few minutes what effect it has on relativistic reflection spectra. So starting with the basic photon trajectories from the disk here, you can see, so from the yellow dot, I simulated photons emitted isotropically from the disk, and color-coded is where they will end up. So the blue lines will go to infinity, the black lines will fall into the black holes, and all of those red lines will actually be bent back towards the accretion disk. They look a little bit crazy and circle maybe a little bit around the black hole, but in the end, they will all hit the accretion disk. And you can summarize this in the plot maybe better, like the fraction of where the photons will end up depending on the radius. And here you can see on the red curve that at the ISCO, almost 50% of the photons for rapidly rotating black hole will actually return to the disk. Most of the other photons will then fall into the black hole, and less than 10% will be actually just directly observed. So those are the photons we previously used for modeling relativistic reflection, or part of it. But what you can also see in the dashed lines are plotted the fractions for a still fast rotating black hole with 0.8, and there are much less photons will return to the accretion disk. So this is very sensitive to the spin and clearly where the inner edge of the accretion disk is. Okay, so we can calculate from both of the contribution, from the direct contribution, now the irradiating flux on the accretion disk. Now using the lamppost geometry as an estimate of the corona. On the left-hand side, you can see the irradiation by a low lamppost at 3RG, and on the right-hand side, you can see the irradiation by a lamppost at a larger height. And in black, I plotted from the flux, I calculate from this direct irradiation, which will be returning to the disk. On the left-hand side, you can see that both of these are quite, I would say, similar, and in part, the returning flux irradiating disk actually dominates the disk, while on the right-hand side, for a larger source, the returning radiation seems not to be that dominant. And we can look into this plot a little bit in more detail. We can actually try to investigate where are those photons coming from that creating the returning radiation. So color-coded is now the emission regions of the photons returning to the disk. So blue is like the very inner ring, and then the other colors up to red are like the outer rings of the accretion disk. And the most interesting here is the blue curve, and you can see here that this dominates regardless of the lamppost height, the returning radiation. And this means that the main effect of the returning radiation, this might be something to remember for you, is that the flux is returning from the inner part of the accretion disk like to the whole and more or less the outer accretion disk. So that's what's happening here. Exactly. And if we now add up the direct flux and the returning flux, we can get some estimate of the emissivity profile, which we're also fitting with our models. And this is plotted now here for a very rapidly rotating black hole and for a little bit lower spin. And you can see, so the dashed lines is without returning radiation. The solid line is now including returning radiation. And while you see that, especially for the high spin case, the normalization is quite different. So the returning radiation adds a lot of flux to the observed emissivity. The shape is still quite similar, I would say, especially for the low height. So you can't really distinguish a height of 2 or 4 Rg in this case. And for a little bit lower spin, you see that the returning radiation doesn't have so much of an effect. So I implemented the returning radiation in the relic cell model. So there's a little bit more to it than just changing the emissivity profile, which you'll have to read up or ask me. I can't go into detail here. And clearly it's implemented in a full relativistic reflection spectrum you can see in the plot on the right. But if you look on the left and just the broad line, you can see a little bit what the returning radiation does. For example, looking at the yellow curves, the dashed line is again without returning radiation, and then the solid line is including returning radiation. And mainly the normalization of the line is changed here, while the shape still remains quite similar. And you can see if you're going to the blue curve, which is for larger height, the returning radiation again doesn't have such a big effect. So I want to present 2 main conclusions we can draw from that to you. First of all, I'd like to look at the reflected flux. This has been touched upon by Andre yesterday already, who rightly said that for a low height corona, you would see quite a low reflected flux due to the gravitational redshift. And this is what's plotted here. So I plot for the lamppost height, I plot what observed reflected flux, not the direct, the reflected flux we observe. And this is kind of what we expect. So that is known. But if we add now the returning radiation, you can see that really boosts the flux actually here, because a lot of the flux which is lost can be recovered by photons now irradiating the outer part and then being observed. So that's quite a huge effect. So I would say here the reflected flux is almost independent of the height if you're now not talking about heights lower than 2 Rg in this case. And we can actually take this one step further and fold in the predicted primary corona flux, because this is what we often measure as the reflection strength, which is the ratio of the reflected to the direct coronal flux, in this case taking it 20 to 40 kV. And without returning radiation, it more looks like this for an inclination of 45 degrees, which is like if you have a low height source at 2 Rg. If you increase the inclination, this could be increased here. But what I want to show is what you're expecting now. If we add the returning radiation, then also the reflection strength is strongly boosted for the low source heights. And I think that's very interesting, actually. So we've seen a lot of reflection-dominated sources, and there have been a lot of discussion about this, and also saying, well, the lamppost geometry or simple geometries like the lamppost or any other geometry cannot explain this easily. But I think if we're including returning radiation and say the spin is high, we can actually easily explain it. The spin just has to be high and the disk maybe a disco, but in principle it can be explained. Yes, and as a second conclusion, I want to briefly show, we did a study here in this publication also to simulate the bias that we had in the parameters by neglecting returning radiation before. So we simulated an HEN spectrum, including returning radiation, and analyzed it without it, as we did before. So the blue lines in
Thomas, 2 minutes.
Okay, great. So the blue lines in this plot here show the values we put in, and the red ones are the one we recovered from the simulation. And you can see, well, in the middle panel, the spin is unaffected, which I think, well, that's great. A little bit expected from what I showed before, because the line profiles didn't change much. The reflection fraction has been overestimated. That's connected to the previous point. And the height behaves a little bit interestingly. So it also has been overestimated for low heights. And that is also an interesting point. So Andre yesterday showed that we have a few measurements published where the height of the lamppost source should be lower than 2Rg. And I'm now telling you we even overestimated that. So that creates even a bigger problem for these kind of sources to be explained. So we'll have to find a different explanation for this. So I'll come to wrap up here. So I hope I can convince you that returning radiation actually dominates reflection for extreme values of spin and compactness, but it's already important for already high spin and compact corona here. And the main effect is that photons from the inner disk return to the outer disk, which leads to a flattening of the emissivity profile, increases the reflection strength. And basic conclusions can be drawn from that is that, well, reflection-dominated sources, in my opinion, can be easily explained once you include returning radiation, but they cannot explain the very steep emissivity profiles required by some observation. It's rather almost contradictory. But I think this brings us maybe closer to a real physical model if we're able to distinguish that. And spin measurements seem to be unaffected by adding returning radiation, as the shape of the relativistic broadening doesn't really change significantly. And as a very last point, I would like just to stress about the returning radiation, that this is not another fudge parameter. You can say we have 50% of returning radiation or whatever. So if we have a high spin and say the disk is at the ISCO, then there will be returning radiation, and we can directly predict it. And so, as I said, I added this in the Relxon model, and I have a paper submitted. And as soon as this is accepted, I will also publish the new version of the model, and all of you can use it. And thank you. And I'm interested in your questions now.
Thank you very much, Thomas. And let's see, I see one question in the, I'm just looking quickly. Okay, let's start with Asaf, who has his hand up, and then if there's questions in the room, let me know.
Okay, so thank you. My question is, what are you assuming about the geometry of the corona? Are you assuming just a point source, or are you assuming something which is a bit more complicated?
Right now, I'm just assuming a point source, but well, in the end, I use it just to model kind of the steep emissivity profiles we're seeing. So all of this would not change much if you use an empirical steep emissivity profile.
All right, thank you.
There is a question in the room.
Okay, please go ahead there.
Your reporting. I would like to ask if you assume not a lamppost geometry with the source at this axis of the black hole axis, but more physical, maybe as a corona away at some 3-5 Schwarzschild radius, would the result change, or at what spin this returning radiation would be important then?
Clearly, if you move the source away from the axis, it would change a little bit. And the returning radiation there would be less strong, because all of what I'm calculating or what I'm using with the lamppost assumption is that we have a lot of radiation primarily irradiating the inner part of the accretion disk. And if this is less, then the returning radiation will also get less. But still, the message is, if you have a really high spin, the disk is close at the ISCO, then you will still have a significant impact of the returning radiation in this case.
And I see we have a question from Anjay.
Hi, so at least in hard states, the observed reflection is weak. On the other hand, if you include this returning radiation in the lamppost model, you get reflection-dominated spectrum. So I think it is another argument against this lamppost with untruncated disk, at least for the hard state. So do you agree?
Yes, I agree. I mean, but this just should serve as a proper physical model to describe the spectra, and then we'll see in the observations.
Yeah, okay, thank you.
How are we looking in the room? Do we have any questions there?
No.
Okay, then, so that was a no. It's hard to hear. Yeah. Okay, then let's go to Oliver, and then I think that's the last one.
Hi, thank you. Do you hear me now?
Yeah.
Okay, excellent. Thanks. I had maybe a bit technical question, but yeah, so I'm still interested. So since this depends on geodesic structure, how does this returning radiation fraction depend on the orientation of the spin with respect to the disk?
So the returning radiation, how it's calculated itself, I think doesn't depend much on the orientation. But clearly, if we're assuming like the lamppost irradiation of the disk and so on, that certainly depends on it. Okay. However, we're just considering really the inner part of the disk, which play a role here. So
Yeah, but the geodesics, like, I mean, they change if you change the orientation.
Yes, it will certainly change a little bit. So we use a perpendicular spin axis to this. Haven't looked into that.
Yeah.
Okay, thanks everyone. I think we need to move on. So let's thank Thomas again. And